Welcome to today's Explainer. Okay, so today we are unpacking a really fascinating but kind of painful paradox. You know the story. Every single year, you got these absolutely brilliant engineers, people who totally crush Kaggle competitions, they know neural net architectures like the back of their hand, and they just completely bomb their machine learning interviews. It's rough. So let's figure out exactly why that keeps happening and, more importantly, how you can make sure it doesn't happen to you. Seriously, why do they fail? It happens all the time. And the core reason is actually pretty simple. These interviews just aren't academic exams. They're not testing if you can memorize some obscure algorithm or, maximize accuracy on a completely pristine, perfectly clean data set. No way. Instead, they're evaluating a totally different cognitive skill set. They want to see how you handle systems, strict constraints, and actual messy, real-world engineering trade-offs. All right, so here's our roadmap for making that shift from notebooks to production. First up, the ML interview paradox. Then data first, models second. Next, mastering the ML toolkit, followed by designing real ML systems, the 2025 AI roadmap, and finally, thinking like an engineer. Let's get right into it. Starting us off, Section 1, the ML interview paradox. So the fundamental misunderstanding candidates have is what the interviewer is actually evaluating in the first place. Look, they don't just want someone who can pick out a fancy algorithm. They want to know, without a doubt, can you safely own an ML system in production? It's all about responsibility and operational realism. You can see the stark contrast here. Junior candidates usually walk in with what we call a modeling exam mindset. They're obsessing over maximizing accuracy using isolated tools, usually in a Jupyter notebook. But senior candidates, they anchor everything in production realities. They're prioritizing things like latency budgets, making sure those P95 response times actually stay under 40 milliseconds. They're talking about managing data drift, building robust pipelines, and figuring out fallback behaviors when a model inevitably just fails silently, because we all know it will. Moving to Section 2, data first, models second. Honestly, if there's one single place where the vast majority of candidates completely wipe out, it's right here. They obsess over the model architecture and just completely ignore the data. But it's an industry staple that 80 to 90% of ML failures originate from data issues, not model issues. Think about that. That is exactly why interviewers have loved deploying data tests. Because if you just jump straight into choosing an algorithm without interrogating the dataset's quality, its schema, or the labeling process, well, you're basically screaming that you aren't production ready. The dataset is the actual engine of machine learning. Understanding it is absolutely paramount. Now, you've got several silent killers when it comes to ML systems. We're talking label noise, data drift, sampling bias, feature instability, the whole shebang. But I really want to highlight temporal leakage here. This happens when future information accidentally kind of sneaks its way into your training data. It's literally like using tomorrow's rainfall data to predict today's weather. Of course, that's going to drastically inflate your offline performance. It makes your model look like an absolute genius in the lab, but it virtually guarantees it's going to crash and burn once it hits production. Really strong engineers proactively hunt for these silent killers before they even think about touching a model. All right, Section 3, mastering the ML toolkit. So when you finally do get to the actual code, it's all about using your tools properly in a real, robust production environment. We aren't just writing simple, isolated scripts anymore. Let's zoom out a bit and look at how a unified pipeline actually prevents that dangerous data leakage we were just talking about. Say you apply a pre-processing step, like scaling, to your entire data set before you split it. Well, guess what? You've just accidentally leaked your test data right into your training set. Big mistake. But by unifying that data split, the pre-processing transformations, and the estimator fitting all into a single pipeline, you make absolutely sure your cross-validation is evaluating unseen data correctly. And hey, strong engineers also know how to optimize hyperparameters without completely burning through the company's cache. A junior engineer might just default to an exhaustive grid search CV, right? That evaluates every single parameter combination and racks up some massive compute costs. But production mindset, they look for smarter alternatives, like randomized search CV, which samples from a distribution, way more budget-friendly. Or, better yet, successive halving techniques. These basically act like a tournament. You evaluate your candidates using minimal resources first, rapidly eliminate the weak ones, and only scale up your compute for the parameters that are actually performing the best. Which brings us to Section 4, designing real ML systems. Tackling an ML system design problem is a whole different beast compared to a standard coding test. You really have to structure a solution end to end and think about how every single piece interacts. Looking at this 9-step formula, you naturally start with problem formulation, picking your metrics and architecture, steps 1 through 3. Then you move through data collection, feature engineering, and model dev. But pay really close attention to steps 7 through 9, building the prediction service, implementing online testing, like shadow deployments, and setting up scaling and monitoring. Interviewers absolutely obsess over these final steps. Why? Because this is where models actually survive in the wild. Showing this kind of structured, big-picture thinking is exactly what hiring managers are hunting for. And of course, we have to acknowledge the massive shift happening right now with generative AI. Designing systems around Gen AI introduces entirely new dynamics to the whole process. You have to weigh different knowledge strategies, like knowing exactly when to use retrieval augmented generation or RAG for constantly changing knowledge bases versus when to use fine-tuning for very specific behaviors. It's a totally different ballgame now. You aren't just evaluating accuracy anymore, you're actively managing long context windows, orchestrating tool calling, and, crucially, building really robust guardrails and evaluation metrics to keep hallucination rates in check and control those massive API costs. All right, Section 5, the 2025 AI Roadmap. Look, if you actually want to build these skills systematically, all the way from foundational math right up to team leadership, you really need a blueprint. Just consider the sheer scope of the modern AI engineer for a second. The demand for this specific role has literally skyrocketed 300% recently. The market right now, it doesn't just want isolated researchers who sit around studying theory. It desperately demands professionals who can integrate APIs, architect full applications, and actually build real, usable products. So to get there, you follow a pretty clear progression. First, you build your foundation in programming, math, and core ML during phases 1 and 2. From there, you essentially cross the chasm into MLOps and data infrastructure in phases 3 and 4. That is where you actually learn to deploy models reliably. Finally, you pick a specialization, maybe LLMs or computer vision, and you cap the whole thing off with leadership and AI ethics. It is a complete, end-to-end journey from raw execution all the way up to architectural ownership. Finally, Section 6, Thinking like an Engineer. Ultimately, you can have all the technical knowledge in the world, but it really won't save you if your communication is completely scattered. Having clear communication and highly structured thinking, those are the ultimate differentiators between a junior candidate and a senior engineer. You absolutely have to avoid the stream of consciousness trap. You know what I mean, when an interviewer asks an open-ended question and nervous candidates just start talking, listing literally every tool they've ever heard of. Please don't do a brain dump. Interviewers want to hear a highly intentional, structured reasoning path where you actively prioritize risks, navigate through ambiguity, and highlight system constraints way before you ever propose a single model. So I'm going to leave you with this final thought. Are you just building a model, or are you engineering a system? That single question really summarizes this entire cognitive shift we've been exploring today. So the next time you sit down to solve a problem, whether that's in a high-stakes interview or just at your desk, I challenge you to step outside that isolated notebook, really embrace the messy, difficult constraints of production, and focus your energy on engineering a resilient system. Thank you so much for joining me on this explainer. And hey, good luck out there mastering the ML engineering mindset.